Kia ora tātou, welcome to this first video where we're looking at kinematics for level 2 mechanics, acceleration in a straight line, part 1 of our kinematics equations. So there's 4 kinematic equations that we need. These are the linear kinematic equations. So linear meaning we're just having motion in one straight line and the acceleration remains constant. So with these equations, there are 5 variables that you'll need to know. So v standing for velocity and then f standing for final. So both velocities are in meters per second. So if you get any distances or any time that are not in those units, you'll need to convert them to either meters or seconds. Distance in meters, acceleration, meters per second, and then time in seconds. So these are the equations again, and we will have a look at this question and go through a process for how to answer them. So if you'd like to first of all read the question, just pause the video, see if you can work it out yourself before we go through, and then we'll go through the steps. So this question has a softball, we're talking about a softball game. A stationary player accelerates from home plate to first base. The player takes 6.61 seconds to get to first base and arrives moving at 5.45 meters per second. So show that the average acceleration is 0.825 meters per second. Just a note on that, anytime you see a show question, it gives you the answer, but you cannot use that answer when you're doing your calculation. So you need to be showing which formula you use, substituting in the numbers to make sure you get that as an answer. And if you don't get that as an answer, you can try again. So it's quite a good way to build your confidence with the questions. So step 1, identify all of the variables that you know. There should be 3. So we're looking for 3 of those 5 variables that they give us in the question. So if you see the words from rest or stationary in the question, that indicates that the initial velocity is 0 meters per second. So here we go, we've got a stationary player, so the velocity initial is equal to 0 meters per second. From home base, the player takes 6.61 seconds, so time equals 6.61, and arrives moving at 5.45, so VF equals 5.45 meters per second. So we can write that down a little bit neater down here. So VI equals 0, VF equals 5.45, and time equals 6.61. Excuse, I'm not using units to save a bit of time. Okay, identify the variable that you're trying to find out is the next step. So here it says show the average acceleration. So that is what we're trying to work out. So acceleration is the thing that we do not know. Okay, identify which equation contains all of the variables. And a bit of a cheat way that I do this is that I use so there's 5 variables and there's one that will not be in the ones either that you know or that you're trying to find out. And in this case, it's distance. We don't want an equation using distance. So you will notice that 3 of these equations contain distance and one of them does not. So here we go. This is the equation there that contains distance. This one, doesn't contain distance. All of those contain distance. So that's my quick way of knowing that these must contain all the variables that we need. And that's the same with every other variable except for VI. You'll notice that the initial velocity is in each one of those equations. So we're using VF equals VI plus AT is the equation that we're using. VF equals VI plus AT, and then solve the equation. So we can do this 2 ways. So you can plug in the values that you know. So VF is 5.45, so 5.45 is equal to 0 plus the acceleration, which is the variable we're trying to find out, times 6.61. So we can rewrite this now. 5.45 is equal to 0 plus, so we don't need to worry about that. 6.61 times acceleration. So acceleration would, if we divide both sides by 6.61, we would get 5.45 divided by 6.61, and then we get our answer, which is 8.1 8.25, or unrounded was 8.245 meters per second per second. The reason we need to use 3 significant figures in this case is because all of the values in the question were given to us in 3 significant figures, so we can't go any further than 3 significant figures for our answer. So that's how we do the first one. Okay, we'll look at another question and see if you can work that out. Although before we do that, let's have a look at another way of doing this to rearrange it. So VF equals VI plus AT. So this for me is a slightly cleaner way of working out the answer, but maybe a little bit trickier. We just need to do the opposite of any operation that we have. So this is plus, so we're going to go VF minus VI is equal to AT. We're trying to work out A, and there's with algebra we know that there's a multiplication in between any variables written like that, so we're going to go divided by T to do the opposite, divided by T. So A equals VF minus VI divided by T, and then we can easily plug in the values there, but we would still get the same answer. Okay, on to the next question. So, calculate the maximum displacement between the home plate and first base. So displacement, we're talking about distance. So let's have a look at the question again. So, except that we're doing displacement this time, so don't need to worry about that. So, D, we're skipping to step 2. D, we are not sure of. So we could actually, now that we've worked out the acceleration from the previous question, we could actually use either acceleration, VF, VI, and T. We know all of those things, and we only need 3 of them. I would recommend using an equation that uses these 3 variables because there hasn't been any rounding errors. Whereas with the acceleration, we had to round that to 0.825. So if we don't use that, then we don't need to carry on any of those rounding errors. So let's have a look at this. We've got VF, VI, and T are the variables that we know. Displacement, D, is the variable we're trying to find out. So we can work out which one of these does not have A in it, and we could use this equation here. So D equals... Oops. No. D equals VF plus VI, we're just going to keep that raw, I'm not even going to edit that out, times T. So VF again was 5.45, VI is 0, so we can go that divided by 2 times 6.61, and we get 18.01. Or 18.0 meters should be our answer for that. Okay, let's look at one last question, and we'll try and get this done in 1 minute time. So you can pause the video and see if you can get these 2 questions done, and then come back for the answers. So step 1 for this question, show the velocity after 0.6 seconds. So we've got time is 0.6, so I'll do it down here, t equals 0.6. Alex and Joe have decided to take a road trip. They start from rest, so perfect. Initial velocity is 0, and accelerate at 4.2 meters per second. So step 1, these are the variables that we know. Step 2, what are we trying to find out? We're trying to find out their velocity. So we're trying to work out VF. Is a question mark, although our answer should end up being 2.5. So we could just go to our equations and work out which one we're going to use. So which one has time, initial velocity, acceleration, and final velocity? In other words, which one doesn't have distance again? And we're going to use this equation there. So we don't even need to rearrange that. We can go VF equals VI plus AT. So 0 plus 4.2 times 0.6, and lo and behold that equals 2.5, and actually it equals 2.52, but like I say, because we're given 2 significant figures in the question, we can only actually give our answer, otherwise we're doing false accuracies. We can only give our answer to 2 significant figures. Goodness, why is this happening? Okay, equals 2.5. seconds. Okay, the next question. I normally try to keep the videos under 10 minutes, but this has crept over. While traveling at 50 kilometers an hour, Joe sees a pothole in the road 15 meters ahead. She must reduce her speed from 50 to 20 kilometers an hour to avoid damaging the car. If the time needed for safe braking from 50 to 20 is 2.3 seconds, show by calculation whether there is enough time to complete the braking before the pothole. We should start by showing that 50 kilometers an hour is equal to 13.89 meters per second. So they've conveniently led us in the right direction there in terms of changing the unit. So like I say, we need to use the SI units anytime we're doing an equation. So the way that I would convert 50 kilometers an hour to meters per second is by, that should be an H, is by first of all converting it to meters per hour. So how many meters are in a kilometer? There's 1,000. So I could change this into 50,000 meters per hour. That's how far it's going to travel in 1 hour. And then to convert it to meters per second, so just to show you, I've times that by 1,000, we can divide it by the number of seconds in an hour, which is 3,600. And so when we do that, we would end up with 13.8, and then it goes on for a while. 89 meters per second minus 1. But I say it goes on for a while, it's recurring. Okay, so that's how we do that. So then to do it for the 20 kilometers an hour, we times it by 1,000 again, so 20,000 meters per hour, and then we divide it by 3,600 and we get 5.56 meters per second. Okay, so we have got we can go back to step 1 now. Step 1, we've got our VF, which is 5.56. We have got our initial velocity, which is 13.89. The time it takes, so this is the tricky one. So there's a road 15 meters ahead. She must reduce her speed from 50 to 20 to avoid damaging the car. The time is 2.3 seconds. So what we're trying to work out is, if we do step 2, the distance is, with these variables, we're trying to work out, will the car be able to stop within 15 minutes? So if within 15 meters. So if our answer is greater than 15, then we'd say no, it's not able to safely stop. If it is less than 15, we would say yes, the car is able to safely stop. So it's just the same as the previous process, but we just need a little bit more working out to get there. So which equation do we use? We don't have acceleration, so we're going to use this one here. Distance equals VI plus VF divided by 2 times t. So we don't actually have to do any rearranging, which is convenient. VF divided by 2 times t. So what we get is 22.3 meters. So you can see that that is greater than 15 meters. So we would say that, go back to the question, we would say that no, there is not enough time to complete the braking before reaching the pothole, because I would need 22.3 meters to brake successfully. Okay, I hope that helps. That's the first video on kinematics, just looking at acceleration in a straight line. Next video we'll look at free falling. Thanks very much. Like and subscribe for more videos. Ka kite.